Hello everyone. Mm, Today we choose one topic, that is the half and full adder and half and full subtractor. Previously in number system topic we seen the basically what is the addition, what is the subtraction, multiplication, all that things already we seen. But here we using of some logical circuits, we have to learn that is the half and full adder, and next part that is the half and full subtractor. But before the moving towards the basic things, then adder is a digital logic circuit in electronics that implements addition of numbers in many computers and other types of processors. Adders are used to calculate addresses, similar operations, and their some operations in the ALU and also in other parts of some processors. In many numerical representations like XS3, some BCD numbers, address are classified into two types. We are referring that all the code conversion in next part, that is basically classified in two types, that is the half and full adder. The half adder circuit has an two inputs, A and B, which add two input digits and generate the outputs carry and sum. The full adder circuit has three inputs. We'll see the stepwise. The next slides are giving the some diagrams also. Uh, an adder is some digital circuit that performs some addition of numbers, and the half adder adds two binary digits, that is called as agent and addend, and produces two outputs, that is sum and carry. Here XOR is applied to both inputs to produce carry. In full adder 3 adds 3 bits. Here 2 can be referred to as operands and 1 can be referred as a bit carried, and produces 2-bit output, that is the carry and sum. This is the some index from today's lecture, that is the adder, half adder, full adder, subtractor, half subtractor, full subtractor. Basically, we before going to the adder and subtractor, mm, we know the basic things. What is the adder and subtractor? The adder is a digital logic circuit in electronics that implements some addition of numbers. In many computers, some kinds of processors, adders are used not only the some ALU operations, but it also used in some processing purpose, as well as used also for the some calculations purpose, some increments and decrements, some operators, and some similar operations related to that. And it will classified, already we told that classified in half adder and full adder. Let us before going to the half and full adder, we have to look here the what is the additions of single bits. Here we taken the 0 plus 0. There are two bits, but 0 and 0, it is the value is the 0, hence we taken the 0. 0 plus 1, it is the basic addition, that is the 1, because 1 is the highest number. And 1 plus 0, that is the 1. Here 1 plus 1, here will get 1 0, that is the 1 plus 1 is the 0, but carry will be generated 1 because in binary number it works only from the 0 and 1. Now main part will start, that is the half adder. It is some simple additions by the two signal binary digits A and B, and it having the two outputs, that is the sum and carry. And the carry signal represents an overflow into the next digit of multi-digit additions. And in half adder circuits are the circuits that perform some arithmetic operations. It adds some two single binary digits and two outputs, that is sum and carry. This is the truth table of the half adder. That truth table till as per the addition, basic addition we shown in previous slide. That is inputs we are given here 0 0 0 1 1 0 and 1 1, and outputs we are taken here sum and carry. The 0 0 when input is 1, the output will be generated 0 and carry also 0. 0 plus 1, the output is the 1, no carry will be generated. 1 plus 0, that is the sum will be 1, means output will be 1, no carry. But here 1 1 will be generated, uh, carry will be generated since we taken the sum 0 and carry 1. From this, the output of 1 of 1 0 is carry out. Sum is the normal output and carry is the carry out. Now it has been clear that the 1 bit adder can be easily implemented with the help of XOR gate, output sum and AND gate for the carry. Using of that truth table, we putting the values. The A and B is the input. We first taken the K map for the sum and second one is the K map for the carry, and we putting the values in K map. A and B is the input. This is the two variable K map 0 1 0 1. The 1 1 will be present. That in here is the no any pair, hence we prepared one given the indication of that K map. In carry only one is the present. See given here. And after reducing the equation using of some Boolean classification, that is the first, this is the marked one in horizontally, that is the 0 is the present means A bar, and vertically 1 is the present means that is the B, means the equation will be gets A bar B, that is the A bar B. And here we when you get it, here is the horizontally 1 is the present means A, and vertically 0 is the present means B bar, means A B bar. This what happen, we got the equation A bar B plus A B bar, otherwise A B bar plus A bar B. This what happen, this is the law of XOR law, that is the A XOR B. This is the Boolean law. In carry only single one is the present, means vertically C 1 is the present means B, horizontally 1 is the present means A B. This is the truth table of the, sorry, K-map of the pattern. In analyzing the results, there are two inputs, two outputs, that is sum and carry, and B in sum can be obtained by using XOR gate, that is we already seen, and carry only one will be generated, hence we are having the AB means and logic gate. And using of that you have to prepare the logical diagram. Here A XOR B, that is the sum, and A and B, that is a carry. Before going to the full adder, I will play the basic video. It will be clear the what is the actual half adder. Then we go to the full adder. Now, I think this link problem is there. We will continue the next part, that is the full adder. In full adder, full adder is an arithmetic circuit that adds two bits and carry, and output will be some bit and carry bit. When you want to add two binary numbers, each having two or more bits, that is the LSB bit signal, can be added by using of half adder, and carry resulted from the addition of the LSBs. The full adder adds bits A and B and the carry from the previous column, called the carry C in, that is the input, and output the sum bit and carry bit, called as the carry out C out. Here also given some details. The full adder adds binary numbers and accounts for values carried in as well as out. The main difference between up adder and full adder is the full adder has three inputs and two outputs. That is the 1 bit full adder adds three 1 bit numbers, that is the A, B and C in, and it has two outputs, that is the sum and that is the carry out. The truth table shown here. That here is the three inputs and we have to record eight variables. The 2 raised to 3, that is the 0 0 0 2 1 1 1. Here is the input A, B and C 0 0 0. When given, the C out will be generated 0 and the sum will be generated 0. And 0 plus 0 plus 1, in that case sum is the generated 1, carry 0. Here also sum 1 carry 0 because only single one is there. Here will be gets 0 plus 1 plus 1, in that case sum will be 0, carry will be generated because there are two 1 will be present from input side. Here is the sum 0, sum 1 carry 0. Here is the sum 0 because two ones are there and carry 1. Here is also sum 0 carry 1. Here also sum 1 and carry 1 because there are three ones. This is the basic addition, 1 plus 1 plus 1. And that all the values we are putting here in KMap. There is a three variable KMap, means we required 8 cells. And we putting here 8 cells. A and B is the A will be putting here in vertical, in B and C is the horizontal. There is the 8 cells, 0 1 0 0 0 1 1 1 1 0. This is the KMap rule, already in previously seen that. And sum, there is a 4 times 1 will become that 1 0 1 2, is 1 and 2 will be 1 3 0 4 5 6 7, and that value will be putting here 1 1 2 4 and 7. This is the no any chance for the pairing purpose. Yes, we taken the singles, and using of some Boolean blocks, we reducing the equation, and we got that equation. It is x or bx or c. After reducing this equation, we got that equation. Same for the carry purpose. That carry having 4 times 1, but it will be near with and it is having some chance to pairing. Hence, we paired that first pair, that is second pair, and third pair. And after that pairing using of some Boolean blocks, we applied the laws, and we got the equation of the carry, that is AB, A and B, or second bracket, that is the C in AX or B. Otherwise, we also taking the AB plus AC plus BC. As per the convenience, we taking this. This is the some analyzing results in full adder. 3 inputs, it having 2 outputs. That is, the inputs are A, B, C. Outputs are C out. And this is the circuit A, B, XOR. The output will be given for the second XOR, and the third input C will be connecting with AND gate, and A, B will be connected with AND gate, and the output of that will be connected with OR gate. And this is the sum equation. This is the carry. This is the all about the adder and subtractor, half adder and full adder. I will before we stop here, I will play the 2 videos related to half adder and full adder, because our video will be clear the concept in detail, and this is some animated video. And I will play them, and we will check that video, and then we will stop.
Hi friends, we will be talking about the adder circuit. If you have been following our channel, you would remember that we have covered a video which walks you through the addition of binary numbers. Typically, addition of binary numbers gives us the sum term and the carry. If in case you need to revise your concepts of adding binary numbers, the link is provided in the description below. But don't you worry, this video will be sufficient to get the drift of the concept. So, getting back to this video, adders are basic building blocks of any digital electronic device. You can use them to make your own calculator. Adder circuits make arithmetic and logical circuits called ALU to compute the binary addition operation on bits of data. Adders are of different types, starting from half adders, full adders, and ripple carry adders. Let us understand the half adder. The half adder circuit is useful when you want to add one bit of numbers. We all know by now, one bit takes two values, 0 or 1. Let us refer to the classic truth table that we all use when two variables a and b are of 1 bit each. Here sum indicates the value operated upon addition, and carry indicates whether there has been a carry or not by adding the two numbers. Let's add them. 0 plus 0 is 0 with of course no carry. 0 plus 1 is 1 with no carry. 1 plus 0 is 1 again with no carry. However, 1 plus 1, as we know in binary systems, the sum is 0 and there is a carry of 1. Also, there is one more trick to find this. If the number of terms to add contain odd number of ones, the sum is 1. And for even number of ones, the sum is 0 and carry is 1. Now, I want you all to analyze the truth table for sum. We see that when variables a and b are both 0 or 1, sum is 0, and when a is 0 and b is 1, or for a is 1 and b 0, the output is 1. This is the truth table for the XOR gate. Let's present this equation using the XOR gate. Let's take a and b and connect to an XOR gate. The output is the sum term a XOR b. Now analyze the truth table for just the carry section. If you all remember the video on basic gates, this is the truth table for AND gate. Let's represent it using an AND gate, and that's our carry expression. Another way we can find the Boolean expression is by K-map. Let's represent this column which is for the carry using it. We will take a 2-input K-map, the inputs being A and B. Let's update it, group it, and write the Boolean expression. Here 1 is present for A and B. The expression for carry is A and B. Let's update the K-map for sum. Let's group the terms. Well, no grouping here. And write the expression for this term. This is A and B bar since A is 1 and B is 0. So while writing the SOP or sum of products, we represent it as A and B bar. This term here is A bar and B. We will take both these terms and sum them, thus writing the sum of the products expression. A and B bar or A bar and B is nothing but A XOR B, and that is our sum expression. And if you notice the K-map for sum, it is quite peculiar. It represents a checkboard configuration. Here no grouping is possible since the ones are represented in the checkboard style. If you see a K-map like this, simply XOR the terms. In this case, it is A XOR B. You can write the Boolean expression for this and solve it and derive to the same answer. A half adder is built using just 2 gates, an AND gate to give us the carry term and the XOR gate to give the sum term. One more thing to remember is that the half adder does not take carry from the previous sum. The answer to this is that the variables are just 1 bit. Hope you have understood the half adder circuit. In the next video, we will see full adders.
Now I will play the full adder. You check that video. You will clear the concept.
I'd like to start this video by thanking all our viewers for the support and love. In the previous video, we have discussed about the half adder circuit. This video will be about full adder circuit. If you have missed our previous video, you can find the link for the same in the description box below. One of the main drawbacks of the half adder is its inability to add carry from the previous addition to the next bits. This is taken care using the full adder circuit. The full adder circuit consists of 3 input bits and 2 output bits. The 3 inputs to the full adder are A, B and Ci, where A and B are the bits to be added and Ci is the previous carry bit. The outputs are S and Co, where S is the sum bit and Co is the carry bit generated for this current sum. As seen here, let us consider this black box with 3 inputs as A, B and Ci and 2 outputs named as S and Co. The truth table for the full adder is also shown here. We can see that the output of sum is high whenever there are odd number of high inputs, and Co bit is high if at least 2 or more than 2 inputs are high. We will try to derive a Boolean equation for the outputs using K-map. If you have a doubt regarding K-map reduction, there is a video link in the video description that might help you. Let us start by finding out what makes up the S bit. On performing reductions using K-map, we find that S is obtained by XORing A, B and Ci. Similarly, let us also try for Co bit. After performing reduction, CO is obtained as AB plus BCI plus ACI. Now, since we have the Boolean expressions, we can build the adder circuit using XOR, OR and NAND gates. We now have a clear understanding of what is actually inside the black box of full adder. Let us try to implement the circuit for full adder. As seen here, the inputs A, B and Ci are connected to 3-input XOR gate whose output is S bit. AB, BCI and ACI are connected separately to 3 AND gates, and the output of these gates is connected to a 3-input OR gate whose output corresponds to CO. In this manner, one can build a full adder circuit using basic gates. However, one does not need to build such a circuit to use full adder. Full adder integrated circuits are available off the shelf, which can be used for your applications. We hope that you have clearly understood the working of full adder circuit. Do share the video with your friends and peers.
This is all about the half adder and full adder. Already we given the in details by the as well as play the two videos, because video will be clear the concept by some animations they are shown there. Yes, I will play the two videos. I hope I'll clear that half adder and full adder. We will stop here and we will continue the next part, that is the half subtractor and full subtractor, in next video. Thank you.